Okay, so it's recording already. So, um, what I want to explore today is the topic VQE, variational quantum eigensolver, a bit farther. And basically, you're not seeing there yet. I'm just checking. Was the UCC, unitary coupled cluster? That's one of the things that was mentioned that I found. Like, if you check out the other video, I was taking a look at David Kopchik's blog the other day, and this is. So out of the stuff that I was researching afterwards and sort of googling around, I found that the thing with the ansatz, it's really basically uh, something you kind of either know by intuition in terms of what ansatz is the best one to use, or you kind of trial and error. And I think for chemistry related things, the UCC was a popular one used because I want to take a look at this a little bit more. In detail. There was another question. If I go to David, just let me check exactly. This is so you should see now the blog, because there are a couple of things that I wanted to explore. One thing was this concept here, because it's just a notation thing. So because I'm going relatively fast with this, I'm also sort of skipping and ignoring a lot of the maths and a lot of the notation. And I mean, I know the whole thing with the bracket and whatnot, but so in preparing a quantum state, this is what you do with the ansatz. That's what we're going to explore today. And then measuring the expectation value. It's like here, the way David brings it is, there's a way you do these by decomposing that into a combination of Pauli matrices. Because then once you know that, you can basically measure the probability of 0 and 1, and then kind of do these, the frequency of zeros and minus 1. And it's just, I got kind of confused. Maybe I'm just stupid, but it's like, what does this mean to measure the expectation value of H? H is sort of the Hermitian matrix that you're trying to find the lowest eigenvalue of. But that's going to be sort of the next video. So let's focus on these first. And for these, I'm going to go with the just Google UCC. I'll just Google unitary coupled cluster. I think that's what it meant. I have it written on my notes. So unitary coupled cluster. Let's just Google this for a second. So maybe strategies for quantum computing, molecular quantum chemistry. I'll just open them on another tab first. See if the. Let's just go. So read the abstract of this quickly. The variational quantum eigensolver combines the ability of quantum computers to efficiently compute expectation values with a classical optimization routine and approximate grand standard, blah, blah, blah. Application of VQE into the simulation of molecular energies using the unitary coupled cluster ansatz. We introduce new strategies to reduce the circuit depth of the implementation of UCC and improve the optimization of the wave function based on it. Additionally, we propose an analytical method to compute the energy gradient that reduces the sampling cost. Okay. Is there I wanna see what's the UCC circuit. Well, UCC ansatz circuit. Can I just something in archive? Strategy for quantum computing. I'm curious about Google. I haven't really read a lot about Google AI, so maybe. So they have actually this in the paper. Is a strategy for quantum computing molecular energies using unitary? Okay, let's take a look at this. I just because I haven't really stumbled upon a lot of Google AI stuff, and I know that the Google AI team is the one that is actually taking and actually doing stuff with quantum computing as well. So the eventual outcome has the ability to but that's, isn't it the same? Okay. Improve the wave function with machine. I think that's the same abstract I just read. So let's see. Download. It's 23 pages long. Why do I have another mouse pointer in there? Quantum science and technology. I'm just quickly scanning it, see if there's any circuit or anything. Okay, so there is indeed a circuit, quantum device. Circuit is a measurement. Let me just zoom in a little bit. Circuit illustrating the measurement of the term on the Z basis, parameter optimization, gradient evaluation, figure 3. So if I measure the imaginary part of that resembles the gradient, quantum gradient measurement thing, or quantum gradient that I saw in one of the machine learning papers that I was reading a while back. A lot of maths. I think I need a bit of coffee. So I'll be a bit jumpy in the beginning. Okay, so here's some results. Okay, but basically, is there background? What is quantum chemistry in second quantization? It's pretty technical. Classical ab initio approaches to quantum chemistry. Unitary coupled cluster. The shortcomings of this traditional CC answer as described in the previous section can be overcome by redefining the excitation operator to be unitary in an approach known as UCC. Coupled cluster. The total energy of the system is obtained from the variational principle. Well, the answer to variation line spans the same Hilbert space as the original CC answer does not lead to equations which can be tractably solved on a classical computer. To see these, we can examine the BCH expansion of the similarity transformation Hamiltonian. Therefore, there's infinite, and thus there is currently no method for efficiently evaluating the energy and amplitude equations on a classical computer without further approximation. Okay, so this is basically. So it seems like there is something that is already existing in the classical world that has some limitations, and then basically there's a way you can remove those limitations by making whatever a unitary. The problem when you do that is that it becomes unfeasible to evaluate the energy with using a classical computer. But basically with the VQE algorithm comprises 3 initial the wave function by application of the parameterized state preparation unitaries and measure the expectation value. I think I'm getting a bit confused by one thing. Let me just go back to here. Expectation value of H. Another losing value. Image matrix H. Because I think so if we think of H being the matrix that describes how does it's the Hamiltonian that describes how does the energy of the system evolve, then that kind of makes more sense to me, because then I would intuitively understand the state as in that's your model, and then the H is then you apply age, as in like you now transform that model based on those rules, and then you measure. But I don't understand. I don't understand this part in here. Let me. The paper from Google seemed like a good starting point, but let me. Quantum chemistry, second quantization, classical elimination approaches. Seems a bit too. Let's see. Let me see if I find something a bit less technical first. What's in here? Is it the same? PDF. Strategies of quantum computing molecular energies using the unitary couple cluster ansatz. So let me quickly scan that. It's the same paper. Okay. Okay, so that seems to be the thing. Okay, maybe I'll try to then let's try to dive into this a little bit, but it might be a bit too technical for me to understand absolutely everything. So we've got introduction. The solution to the time-independent Schrödinger's equation for molecular systems allows for the prediction of chemical properties, holding the key to materials discovery and catalyst design. Let me just understand that for a second. Time-independent Schrödinger's equation. Despite advances in the field of quantum chemistry, many relevant problems such as the prediction of chemical rates and the description of transition metal complexes remain challenging. These difficulties stem from approximate nature of classically tractable quantum chemistry approaches, which often fail in the description of strongly correlated systems. In addition, the application of exact methods as exact diagonalization of the electronic Hamiltonian require exponential resources with current classical algorithms, so limiting the exact simulation of molecular energies to a system comprising only a few atoms. I've envisioned that quantum computers could provide a tractable way to simulate quantum systems. This idea, formalized by Abrams and Lloyd a decade later, has been developed in the series of quantum algorithms for quantum simulation, 13, 15. The first algorithm extending these approaches to the calculation of this is the first proposal, further developed in 17, combines trotterization of the molecular Hamiltonian and phase estimation to compute the ground state energy of a molecule. Phase estimation in here. Okay. Early studies on the quantum resources required by this algorithm showed that the circuit depth scales. Fortunately, numerical studies indicated that the scaling for real molecules is closer to n to the 6. Okay, where is this all going? If this particle number manifold, the variation of quantum eigensolver is an alternative algorithm that is closer to near-term applicability due to lower coherence time requirements. The VQE algorithm finds the best variational approximation to the ground state of a given Hamiltonian for a particular choice of ansatz. This is achieved by two subroutines. The first employs a quantum computer to prepare a parameterized wave function ansatz and measure the expectation value of the Hamiltonian given a set of values for the parameters. The second subroutine is an optimization algorithm. Yeah, we read that, okay. There's robustness, quantum errors, and small coherence time requirements. Yeah, okay. It was first applied to simulation of molecular energies. In this case, a trial wave function is prepared by the application of a parameterized unitary, followed by the calculation of the energy via Hamiltonian averaging. The calculation of the energy via Hamiltonian averaging. That is maybe. So what is 31? Let me just go back to the top. The value of the energy is minimized using a classical optimization. Yeah. Currently, the final cost of the calculation depends on the amount of iterations required for convergence and the amount of operations involved in each preparation and measurement cycle. chips and traps and superconducting circuits. Okay. Traditionally, a unitary coupled cluster approach has been used as the ansatz for the state preparation. This method provides a hierarchy of wave functions that can be prepared on a quantum computer using a polynomial number of gates and is believed to provide better accuracy than classical coupled clusters, which is generally regarded as the gold standard of quantum chemistry. Despite these advantages, recent studies have pointed out that the number of parameters in UCC might still be too large to allow practical calculations for large molecules. Okay, so we aim to describe in more detail the implementation of VQE approaches for molecular systems using a UCC ansatz. Okay, background. Sounds good. So, let's see. Within the Born-Oppenheim approximation, a molecule is comprised of a system of electrons interacting in the potential produced by nuclei located at fixed positions. We may describe this problem using the formalism of second quantization, whatever that is. I'm really just reading. I don't understand most of the stuff. It's mostly what I'm saying always. But I'm hoping maybe it takes something out of that. An interaction between electrons can be represented using annihilation and creation operations. AP and AP transpose. ASAP P and ASAP P transpose. They obey the following anti-commutation relations associated with fermionic statistics. Needs where the electron mass and the electron charge E, Bohr radius A0, columns constant. We may write. Oh my god. Oh. Spatial and spin coordinate with from mean field. So this is just a way to describe the interaction between the electrons of a molecule. Classical ab initio approaches to quantum chemistry. The inherent difficulty of solving the Schrödinger's equation for many electron systems has motivated the development of a series of standard models for the construction and calculation of approximate electronic wave functions in quantum chemistry. Product of one electron functions. The Hartree-Fock method provides such a single determinant solution. In this scheme, the molecular orbitals are expressed as a linear combination of atomic orbital functions. The combination coefficient are the output of this calculation provides a mean field approximation to the molecular wave function. Unfortunately, the Hartree-Fock method is incapable of approximating the electron correlation effects that are essential for computing energies within or close to chemical accuracy. To correct for this problem, one can expand the wave function as superposition of all the determinants in the electron-Fock space. The coefficients in the expansion can be parameterized in different ways. This is way too deep right now for me. State preparation, measurement. Schematic representation of the variational quantum algorithm applied to UCC answers. The classical operation routine adds the expectation values of the Hamiltonian terms to calculate the energy and estimates a new value for the coupled cluster amplitudes. Implementation of the UCC on a quantum computer. Okay, so this is about how to implement the UCC. So they go about all this crazy stuff in here. The key for the deployment number of operations to perform is to truncate STC expansion. A popular truncation in quantum chemistry is to consider only single and double excitations. And is exact for systems with 2 electrons. If non-local gates are available, an equivalent alternative to CNOT gate specifically developed for ion trap connections is the Moore-Mesurins and MS gate. Its unitary evolution can be represented by the sum over all joint rotations on qubits J and K are the register for an angle theta around the axis phi, which can be freely chosen. Oh my god, the MS gate, what the hell is that? The action of UMS creates a fully entangled state under this thing. This non-local gate can be made to act on arbitrary subsets of qubits in various ways. What is this? Circuit illustrating the measurement of the term. We must apply H or like an X rotation or equivalent to change bases when measuring Pauli Y and Pauli X operations. Once the state preparation has been performed, the next step in VQE algorithm is the calculation of the objective function that corresponds to the energy measurement. To avoid performing phase estimation, which has a prohibitively large circuit depth for current and near future quantum devices, we employ the Hamiltonian averaging procedure. Interesting. So they talk about the Hamiltonian averaging procedure introduced in 31 and 35. In this case, the energy is calculated by measuring the expectation value of every term in the Hamiltonian and adding them to obtain the total energy. Where every Hamiltonian term comprises of a tensor product of Pauli matrices obtained from the transformation multiplied by the corresponding Hamiltonian coefficient. Estimate the number of measurements required to converge the total energy. Okay. So this is done this way to avoid using phase estimation. Okay, interesting, but why would phase estimation work in this case? So it's the Hamiltonian averaging procedure, the one that's used to measure the energy. To avoid performing the phase estimation. Why you want to avoid performing phase estimation, which has a Hamiltonian averaging procedure copy in 31 and 35. So what is the Hamiltonian averaging procedure? that is going way beyond so far. I feel I'm stepping kind of right at the edge of my capabilities. Opened the box a little bit too much. So the UCC, it's clear that the way it's explained here, I can't really grasp quickly. Need to deep dive into this a bit more calmly. This measurement thing is what I don't yet grasp. Coffee. Okay. UCC for dummies. Nah, that's probably it. Uniform commercial code. That's not what I want. What is that? Unitary coupled cluster. Unitary coupled cluster. Example. Coupled cluster. Quantum implementation of unitary coupled cluster. Let's take a look at this. 2016. Bum, 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 bum. Bum, 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 bum. Grade. So, in classical computational chemistry, the coupled cluster ansatz is one of the most commonly used methods, which is critically limited by its non-unitary nature. The unitary modification as an ideal solution to the problem is, however, extremely inefficient in classical computation. Here, we provide a first experimental evidence that indeed the unitary version of the coupled cluster ansatz can be reliably performed in physical quantum systems. A trapped ion system. We perform a simulation on the electronic structure of the molecular ion HEH+, whatever that is, where the ground state energy surface curve is probed. Energies of excited states are studied, and the bond dissociation is simulated non-perturbatively. Okay. So, what is A doing? The conceptual procedure and BF, the experimental realization of the UCC simulation to find the ground state of the target molecule. Hamiltonian of the target molecule. H. Mapping to quantum system. Preparing trial quantum state by UCC ansatz. Measuring the energy of the state. Is it the minimum? No. Adjust the parameters. Prepare another quantum state and apply the Hamiltonian. Yeah. Minimum ground state of the target Hamiltonian is found. Measurement of energy. Oh my god. Why is this so complicated or weirdly explained? Experimental realization of the unitary coupled cluster ansatz. that's the same paper. What does the Wikipedia say? Coupled cluster is a numerical technique used for describing many body systems. Its most common use is one of several blah 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 ab initio quantum chemistry methods in the field of computational chemistry. Coupled essentially takes the basic molecular orbital method and constructs a multi-electron wave function using the exponential cluster operator to account for electron correlation. Some of the most accurate calculations for small to medium-sized molecules use this method. The method was initially developed by Fritz Koster and Heinrich Kümmel in the 1950s for studying nuclear physics phenomena, but became more frequently used when in 1966 this guy and later together this other guy reformulated the method for electron correlation in atoms and molecules. It is now one of the most prevalent methods in quantum chemistry. That includes electronic correlation. This is called coupled pair method. Wave function ansatz. Coupled cluster theory provides the exact solution to the time-independent Schrödinger equation, where H is a Hamiltonian of the system. Just double check, because the Hamiltonian represents the energy of the electrons and the nuclei in a molecule. Okay. In atomic molecular, sorry, you don't see that because I have it on another tab. Molecular Hamiltonian. Just double checking that I don't have any big gaps. In atomic, molecular, and optical physics and quantum chemistry, the molecular Hamiltonian is the Hamiltonian operator representing the energy of the electrons and nuclei in a molecule. This operator and the associated Schrödinger equation play a central role in computational chemistry for computing properties of molecules and aggregates of molecules, such as thermal conductivity, specific heat, electrical conductivity. The elementary parts of a molecule are the nuclei, the numbers. Okay, so and E, the exact energy of the ground state. Coupled cluster theory can also be used to obtain solutions to excited states. The wave function of the coupled cluster theory is written as an exponential ansatz. So the wave function is just I feel a bit lost still. Feel a bit lost. Yeah, just because this is really foreign to me. I mean, so what is this one? This is the one I just, this is the one I just saw. Just wanted to get this other one. The one that I found through the Google stuff. Probably should just go through it again. Or keep going through it. Background quantum chemistry. So a molecule is comprised of a system of a set of electrons interacting with the potential produced by the nuclei located at fixed positions. What is the formalism of second quantization? Second quantization. second quantization, also referred to as occupation number representation, is a formula used to describe and analyze quantum many-body systems. In quantum field theory, it is known as the in which the fields are thought of as a field operators in manner. Okay. Too much. So let's go back to this. The method provides a hierarchy of wave functions. No, where was I? The background. Within the Born-Oppenheim approximation, a molecule is comprised of a system of electrons. We may describe this from any interaction between electrons can be represented using annihilation and creation operations. That they obey the following anti-commutation relationships associated. Correspond to classical electrostatic repulsion between nuclei and the constants or correspond to using atomic units or electron mass. Coulomb's constants, nuclear charge, estimation. Nuclear, the function represents one electron function. Spin orbitals are often obtained from a mean field calculation such as Hardy-Fock. After removing the translational and rotational degrees of freedom, the electronic energy of a molecular system is a function of 3q minus 6 parameters that we will denote by R. Then Q is the number of atoms. The function ER is called the potential energy surface. The accurate calculation of PES is one of the main challenges of quantum chemistry, as it is required for predicting and understanding a wide range of chemical processes such as reaction dynamics, bond breaking, chemical kinetics. The prediction of thermochemical properties such as reaction rates and determines accuracy required from ab initio calculations of the PES. So there's the definition of the chemical accuracy. Classical ab initio approaches to quantum chemistry. The inherent difficulty of solving the Schrödinger's equation for many electron systems motivated the development of a series of standard models for the construction of calculation of approximate electronic wave functions in quantum chemistry. There's approximate electron correlation effects that are essential for computing energies within the closed chemical accuracy. So I think that's kind of a key element of the whole thing here. It's basically saying the classical method is not good enough to sort of account for correlation effects. That's why a quantum computer is better at this. To public CI and a couple classes CC methods. Excitations with respect to reference. Essentially chosen to be the Hardy-Fock state. This idea can be formalized by defining excitation operations as follows. So, the key point of establishing the size extensor. So it's clear to me that I'm not going to understand UCC so easily. But I understand more or less where it's coming from. More or less. And it has to do with there's indeed a sort of a superposition. What I found in this paper that was kind of a bit weird is that that the reason for doing this averaging procedure and the measurement is to avoid performing phase estimation. That's kind of, I like to understand a bit more why. I like to understand a bit more this part in here, and what is then the why there's this brat then thing and then this cat thing here. What is it that how is that then the average of the energy? State operation has performed the next step in the VQE is the calculation of the objective function that corresponds to the energy measurement. So next, okay, so I know next, I'm gonna stop here. That's a tough one. That's a tough one. But I'm gonna stay away from the UCC for a second because it's too much chemistry related and less relevant for me, I would say right now. But it's just stick with the fact that it's a good model. But I'm basically still trying to understand sort of what are you doing from a quantum computing perspective, right? So you're preparing that model, and then you're applying the Hamiltonian, because it basically, the Hamiltonian transforms that state, and then you're measuring that. But that measurement is what I'm not kind of trying to understand. Why is this the thing you want to minimize? And why is this has anything to do with phase estimation and versus this averaging approach? So that's what I'm going to try to explore in the next video. The outcome for me for this video is UCC so far makes no sense for me to understand at the technical level because it's chemistry related, and I just have no idea about it. So I would have to build up a lot of other knowledge that I really don't have the time and the sort of the mental effort to put into right now. But it's like the concept. So it's a well-known thing. It's a version of a classical golden standard, and then that works well on quantum computing, on a quantum computer, especially on a sort of a NISQ device, right? But what this is my next thing. So what is this measurement? So what is this thing here, and what is the I keep missing. I keep forgetting that. I keep losing the. So why exactly? Why to avoid? No, where is this? Ah, come on. Oh man, the background. I'll keep the paper linked. Implementation of these. So it's the measurement part, the choice of the proportion, energy measurement. This here. This is what I, to avoid performing phase estimation, which has a prohibitively large. So why would we? I mean, if you can give, if you know anything about it and you're watching this video and you wanna give me a hint, just go ahead. So why would phase estimation even help us to understand that? So what is the why? So it seems like that phase is the thing that we want to minimize. Why? Yeah, cool.